Hey guys, this is section 9.8, osmotic pressure. So first of all, osmosis. The idea is you have a semi-permeable membrane, which actually occurs in nature quite a bit. Semi-permeable membrane is a membrane, a barrier that will allow some molecules through but not others. Common situation, which is what this picture here is showing, is this semi-permeable membrane will allow water to pass through, but not the solute, like sodium chloride or sugar or something like that. And so what you have is on the outside of this membrane, you have pure solvent, pure water, let's say. And inside you have a solution, sodium chloride and water, sugar and water, something like that. So what happens is the water will pass through the membrane, and as it does so, it's diluting the solution in here. Until it comes to equilibrium. Now, as the water passes through the semi-permeable membrane, because the volume is increasing, it's pushing this column up. It's increasing the pressure at the base of this column. That increase in pressure, the difference, is called the osmotic pressure. We'll use the symbol pi for that. So at equilibrium, it must be true that the chemical potential inside of the membrane, which is this term here, is equal to the chemical potential of the solvent outside of the membrane here. We also know from Raoult's law that we can write the chemical potential of the solution inside the membrane as chemical potential of the pure solvent at that pressure, at that mole fraction, plus RT/ln mole fraction of the solvent. Setting these two equal to each other because they're both equal to this term right here. And so saying this is equal to this, we get this equation right here. Now, we also know that the chemical potential is equal to the molar Gibbs energy, or d mu is equal to dgm, and dgm is equal to the molar volume dp minus the molar entropy dt. At constant temperature, which is our situation here, dt is 0, so we get d mu is equal to molar volume dp. Now what we're going to do, guys, is going to integrate this, both sides of that equation, from pure solvent, which is mole fraction of 1, up to some arbitrary mole fraction of the solvent, and from the initial pressure, the outside pressure, to the pressure plus the osmotic pressure. So when we integrate the chemical potential, we just get the difference after minus before. And assuming that the molar volume is independent of pressure, which is a really good assumption for a liquid, the volume will not change very much at all with pressure. We pull that outside of the integral, and we just get P plus pi minus P, which is just the osmotic pressure times the molar volume. The star just means it's the molar volume of the pure solvent. Substituting into the equation we got on the previous slide. So this term, so if we bring this over, we get this minus this is equal to negative RT/ln mole fraction. But this minus this, that term right there, is just equal to molar volume times osmotic pressure. So that gives us a simplified equation. This right here, the molar volume of the pure substance times the osmotic pressure is equal to negative RT/ln mole fraction of the solvent. But now we're going to do some stuff with the natural log. The mole fraction of the solvent is 1 minus the mole fraction of the solute, right? Because there's two components, the solvent and the solute, and their mole fractions must add up to 1. But the natural log of 1 plus x is approximately just x, if x is a lot less than 1. And here, this is going to be a dilute solution, so that means the mole fraction of the solute is a lot less than 1. And so natural log of 1 minus the mole fraction of the solute, it's pretty close to being negative mole fraction of the solute. And the definition of the mole fraction of the solute is moles of the solute over total moles, which is moles of solvent plus solute. But once more, because the moles of the solute is so much less than the moles of the solvent, this is pretty much the same as moles of the solute over moles of the solvent. Now, we're going to take this, okay? Remember, all this is equal to natural log of the mole fraction of the solvent, which is up here. We're going to substitute for this guy right here, When we do that, we get this. The molar volume of the pure solvent times the osmotic pressure equals RT, the moles of the solute over moles of the solvent. Rearranging this, solving for the osmotic pressure, we get this equation right here. Now, the molar volume of the pure solvent times the moles of the solvent is just the moles of the solvent. But that's going to be basically identical to the volume of the solution, because by adding, it's a dilute solution and the solute is not going to change the volume very much at all. So we can just write V down here. And so we get osmotic pressure is equal to RT moles of solute over the volume of the solution, which is the same. The moles over the volume is the molarity. So it's a real simple equation. Osmotic pressure of a solution is equal to the molarity of that solution times R times T.